This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. So let's continue the discussion of the Rankine cycle, which is the ideal cycle or the basic cycle describing the steam power process. So in this cycle, we have four components again, starting with a pump, which is pumping liquid water, raises the pressure into this boiler. Boiler essentially is a device where you can add heat into it, and that happens at high pressure and high temperature as well. And then the pressure is high, you need a device to drop the pressure, right? You're using the steam turbine. Turbine, again, is similar to a gas turbine. We assume it's an isentropic process. And when the pressure is reduced, the temperature is dropped, then you can output the turbine work. Then after that, you're going through a device called condenser, which is essentially just another type of heat exchanger to allowing you to reject the heat from the cycle. So there, the temperature is low and the pressure is low. Because here you're going through a phase change process, a lower temperature means lower pressure. So often, if you consider the 1 atmosphere pressure corresponding to a boiling temperature 100 degrees C. If you want to have the condenser operating at any temperature below 100 degrees C, which means this condenser needs to operate at a pressure below 1 atmosphere, which means this needs to be operated with vacuum. So they become a vacuum chamber. And then you're going the condensed water is going into the pump again. All right. So on the TS diagram, this is a basic TS diagram for the Rankine cycle. And let's quickly go through the calculation. So for the basic Rankine cycle calculation, the typical given is the pressure as well as the turbine inlet temperature. And you only need these three in order to figure out basically everything for this basic ideal cycle. So you're starting with state 1, which is the pump inlet. So from the pressure 1, and this state 1 is right on the saturation liquid line, you would figure out x1 equals to 0. Then you basically figure out everything for that state due to the state postulate. Then you can find the H1 and S1, right? And probably also want to find the specific volume of the water at that state. So that's useful for the next step calculation. And then the S2 equals to S1, right? Isentropic process going through the pump. And then we know the pressure. Then we know the entire state 2. And there you can find H2. And from H2 you can calculate the pumping work, which is H2 minus H1. So that's one way to determine the pumping work. Again, this is an isentropic process, which is by definition is adiabatic. So there's no heat. Enthalpy change equals to the work involved in the process. So this is one way if you can figure out the enthalpy at both states. Another way, actually, you can also using the relation we derived before for a reversible process involving compression work and turbine work. The work can be write as specific volume times the change in pressure. dP, absolute value. All right. So in this case, because we're dealing with liquid going through the pump, the specific volume of liquid or water as a function of pressure is a very weak function of pressure. Essentially, you can consider that one is a constant. Then you can just write V1 and the pressure of P2 minus P1. Right. So that's actually it's a more common way to calculate the pumping work. The V1 is very small. The specific volume of water, liquid has a very large density, which means its specific volume is very small. So this is a very small value. Even times pressure change, the total value is very small compared to the rest energy terms. So the one thing you want to be aware of, the pumping work is a work in the entire calculation, but it's order of magnitude smaller than the heat input and heat rejection, as well as the turbine work, right? So this is a much smaller than the rest energy terms. Even you throw it away, it doesn't cause much error. Although if the problem asking you to calculate, you do not want to throw it away. All right, so that's the state 2. Then to the state 3, we know the pressure at the state 3 equals to the pressure at state 2. Then we know the temperature at the state 3 as a given. Then you can find the H3, S3, and the heat input. Okay, so that's the Q in work pump, work turbine, and the Q out. All right, the Q in equals to H3 minus H2. All right, and then going through the turbine, which means the state 4. You need to figure out the state 4. State 4 is also readily known with the S4 equals to S3 isentropic process, as well as 1 and 4 are on the same horizontal line, which means temperature and pressure are the same, right? For the state 1 and the state 4. So from the P4 equals to P1, you can figuring out the H4. But this calculation is not directly coming from the property table, because you need to decide on this horizontal line where the state 4 is. That is determined by the where this vertical line is, right? So in terms of calculation, just one more step. You need to figure out the quantity at the x4 first. That determines where the state 4 is on this horizontal line. So x4 equals to S4 minus the S fluid and Sg minus the S fluid. So you know this horizontal line. You know the saturation liquid versus saturation vapor in terms of their entropy. Then you can figure out where, and with your knowledge of the S4, you can figure out the X4. Right? So from there, you can determine the H4, which also require one-step calculation, which is X4 times Hg plus 1 minus X4 HF. Right? So this is all straightforward. So the calculation here assume that you end up with the state 4 underneath the saturation dome, which means you are dealing with like two-phase as stated for. What if you calculate the x4 greater than 1? If you calculate x4 greater than 1, which means outside saturation dome, and on the right-hand side, right? Which means it's a overheated vapor. So in that case, if you end up with that situation, in general, that's not the case. So when steam turbine running, it's in general, it's end up with within the saturation dome. But if your calculation showing the problem, in reality, it's possible. It's end up outside this saturation dome. In that case, you need to go to a different property table to find all these properties. The conditions are still known. The entropy is known. Let's say if end up with there, which corresponding to another process over there, right? So in that case, the pressure is known, the entropy is known, the state is known, right? You just go to a different table to figure out everything. All right. So that's the calculation for the very basic Rankine cycle. So with that, we can calculate the efficiency. Which is the net work output versus the heat input. So the turbine work we have is H3 minus H2. The pumping work is V1 P2 minus P1, and the input is H3 minus H4. That's the turbine work. And the heat input is H3 minus H2. All right, so that's the basic cycle. So our main interest is based on this basic cycle, how can we improve the Rankine cycle? All right, that's the topic we're going to discuss today. So improve Rankine cycle efficiency. Rankine cycle, as I said, is used for the power generation, and for power generation, efficiency is one of the primary parameters that you consider. It's unlike aviation. And for gas turbine, if you consider the application of aviation, you more consider of the power to weight ratio, which means the power density. But for the power generation, efficiency, which means more efficient power plant, means less fuel you need to burn, which means the cost is less. Right? So how to improve the Rankine cycle efficiency? So there is two principles or rule of thumbs, which is coming from the Carnot cycle. We recall the Carnot cycle efficiency can be written as Carnot heat engine can be written as TL versus TH, the low temperature reservoir versus high temperature reservoir, minus and by 1. So this one is saying that there are two ways you can improve the, in theory, you can improve a heat engine cycle. If you can increase the temperature of the hot temperature reservoir, which means you make this term larger, you will have a high efficiency. The other one is opposite. If you can reduce the low temperature reservoir, the efficiency will goes up as well. So based on this idea, in a Rankine cycle, the heat addition and the heat rejection process is not constant, right? You're going through a non-constant, non-isothermal heat addition and heat rejection. But the idea is there. It's saying that if you can increase the average temperature during the heat addition, you get high efficiency. Or if you can reduce the average temperature during the heat rejection, you get high efficiency. So that's the idea. So applied to the Rankine cycle is to reduce the average temperature, increase the average temperature of the heat addition, and reduce the average temperature of the heat rejection. All right. So that's the two principles that we can utilize. So we will first discuss some theoretical considerations, then discuss what is being practically used. All right. So let's draw a basic cycle first. So with this basic cycle, if we want to use the first principle, which means to raise the average temperature during the heat addition, one way we can do that is just to increase the T3, the steam turbine inlet temperature. So that's something we can do. For example, if we move this vertical line to the right, we get additional area, which is corresponding to purely work. By doing that, the average temperature from 2 to 3 will be higher, so that we can have a higher efficiency based on the first principle. So the first one we can do is increase the turbine inlet temperature. This is something we have seen before, right? When we study the gas turbine, we said if we can raise the gas turbine inlet temperature, we can get high efficiency. We see that already from the ideal cycle. Ideal gas power cycle there. So this indeed has been used, and similar to the gas turbine cases, the temperature of the steam turbine already being raised to the maximum level that the material can handle. So today the maximum temperature is around 650 degrees C. So already being raised to the limit that the material or steam blade or the boiler can handle. Consider this temperature, if you compare with the gas turbine, much lower, right? Gas turbine is somewhere 1,000 degrees higher than this. The highest one is already over 1,600 degrees C. And the reason for that is, anyone have a different phase, or you're saying that this one is involving phase change? It's related. It's related. If you consider how this combustion process, or how the combustion or heat transfer happens here. A gas turbine is an internal combustion device, right? The gas is directly being burned, so absorb basically all the heat except the heat loss. So it can be raised to the very high temperature. But for a steam turbine, steam is not directly coming from the combustion, right? Steam must be heated by something happening outside the steam tube or the steam generator in order to transfer the heat to the steam, right? So this heat transfer process limiting the temperature that the steam can be generated. And also other consideration is steam is not an ideal gas. It can be corrosive, and particularly if you have high pressure on the high pressure condition. so it cannot reach as high temperature as the gas turbine. But anyway, this is already being reached as a practical limit. One thing we notice is any time that you can increase the turbine inlet temperature, that's something useful in terms of helping turbine to work. That's related to when you shift this line to the right. This the state 4, if I have a prime there, the state 4 prime will have steam will have a lower or higher quality compared to the state 4 without prime. Will be higher quality. The closer to the when you move the state to the right, which means you're closer to this the dome, directly on the dome here corresponding to the quality of 1, right? So when you're increasing the temperature, you shift this turbine line to the right, you increase the steam quality, which is a beneficial thing for the steam turbine to work. So X4 increased, which is good. It's a useful thing. The other way you can utilize the first principle or first rule of thumb to raise the average temperature during heat addition is to increase the pressure. Increase the pressure during the heat addition. All right. So in that case, if we consider that we already have a limit for our turbine inlet, so in this case, if you can raise the pressure, which means when you going through the pump, it will reach a higher pressure line there, right? So in this case, you would have some additional area being gained here, and then you're going down here. So this is basically you raise the pressure up and then reach the same turbine inlet temperature there. So in this case, obviously you increase the average temperature during the heat addition, again, because underneath the saturation dome, the temperature and pressure are correlated. High pressure means high temperature, right? But this case is not necessarily all good. You can have a higher efficiency. Maybe I just raise the boiler pressure. So I should say the average temperature, heat addition temperature increase, the efficiency increase. And similar here, average temperature increase, efficiency increase, right? But raising the pressure has several downsides. One is, as we mentioned now, because you are limited by the turbine inlet temperature, this state of this, let's say 3 double prime there, and this 4 double prime. The 4 double prime now will further into the saturation dome, which means its quality will become lower, which is not good. This is definitely a downside, and also when you're increasing the pressure of the entire system in industry, high pressure means high cost. Pressure, as I said, the pressure is equilibrated at the entire equipment or entire system. So everywhere you need to using a high pressure rating or the material rated for the high pressure in order to handle the whole thing. And also the temperature is higher. The high temperature, high pressure will require the system using more expensive material. So that's not necessarily desired. So it's more costly. But certainly for applications people try to reach higher as much high pressure as possible. And to solving this poor quality problem, there is an additional or modification has been done to this Rankine cycle, which is called the reheated Rankine cycle. And we are going to discuss that in a minute. So one picture I'd like to show here is related to the, if the steam containing a lot of water, condensed water, you can really damage the steam turbine. And as I mentioned before, if you have a liquid flowing at the same velocity as the gas, liquid has a density which is like 1,000 times of vapor. So when they hit the surface, the impact or the damage can be certainly significant. You can consider that if there is a strong wind and blowing towards you, and in the wind there is a sand. Right? Sand is a liquid, which you can, is a solid. You can consider that's 1,000 times of density compared to the air. So that definitely can damage the blades over time. So to maintain the quality of the steam, generally you need to have this X4 above certain threshold, like the 0.9. So X4 is usually greater than 0.9. Do not have more than 10% of liquid. All right, so that's two ways that we utilize the first principle. And another one is to reduce the average temperature during the heat rejection. So that's the third one. Reduce condenser temperature. So in this case, in terms of TS diagram, what you have is you have a lower pressure line and you allow the turbine to expand further down to that line. So in this case, the average heat rejection temperature drops and the efficiency can increase as well. But this, if we want to do this, there is also certain downside. And one, again, is similar to raising the pressure. You're getting further into the saturation dome, which means the X4 steam quality will be decreasing. So that's not ideal. And another one is you cannot reduce this pressure as much as you want. If you consider in the condenser, as we showed last time, the condenser is where steam is condensed to water, release a lot of heat, and that heat needs to be taken away by cooling water, right? Typically by cooling water. So the cooling, how much the cooling water can be cooled is really not, really have a limit. If that cooling water is coming from a flowing river next to the power plant, you cannot have that cooling water below that river temperature, which is ambient temperature, right? So in that case, you have a limit. You cannot lower this line as much as you want. It has a practical limit there. So it's limited by the cooling capacity available. And also, as we said, the lower temperature means lower pressure, which means the condenser will operate at an even higher vacuum level. And when something working under vacuum, what could happen? If you have a vacuum device and you want to work it properly under that sub-atmospheric pressure, and something can happen to yes. You mean you need a vacuum pump to draw the whole thing? That not necessarily. If you consider this is a phase change, if the temperature is low, the pressure is low, will low by itself. You need to produce the vacuum in the first place. But after that, as long as the container is sealed properly, it will maintain that vacuum. One practical problem is the container is not perfectly insulated. The more vacuum it operates, the more likely it will leak, right? So any small crack, which is fine on the low vacuum condition, or on the high vacuum condition, it will start to leak, right? And when air leaking to the system, is that okay or not okay? Air is cannot cause explosion in the process, right? You don't have fuel involved, but the air is not part of the water or part of the steam. It will not go through the same phase change process, right? Air will not condense in your system. When steam condensed water and air is there as a liquid, and when you're going through the pump has to pump liquid and gas air at the same time, which is not ideal. So another practical practical consideration is more likely to leak. Right. So this basically is a three. Based on the consideration from the Carnot cycle, there is three ways that we can improve the Rankine cycle efficiency. But what I'm going to discuss next is what actually being used in reality. As said, in the turbine inlet temperature has already been used to the maximum it can be. This lower the condenser temperature or pressure that's limited by the practical considerations. So the main thing is related to raising the boiler pressure. I should say the boiler pressure nowadays is almost 300 bar maximum. 300 bar is very high pressure. If you remember the critical condition for water we mentioned before, for critical water critical point is 220 bar in terms of pressure. In terms of temperature is 374 degrees C in terms of temperature. So if you're looking at these two conditions combined together, the maximum temperature and the maximum pressure both are higher than the critical point, which means many of the modern steam power plant actually operate with the supercritical water. So the boiler generates the supercritical water and then going through turbine and then going through condenser. So in terms of TS diagram here, it's a line which is going up and then going down. It does not, you don't have a horizontal line. You don't have a distinctive phase change step. You're just going there and then going down. So that's the so-called supercritical steam cycle. All right, so in terms of raising the pressure, we said raising pressure needs to be used together with a process called reheating or reheated Rankine cycle. I'm not going to draw the schematic, but it's basically showing here. The reheating is saying that the main purpose of the reheating is to get rid of the low steam quality problem, to avoid there too much moisture at the end of the turbine step. So what happens here is you have the typical one from the state 1 going through the pump, then going through the boiler, and the turbine, you have a two-stage turbine, the high pressure one, and after the high pressure one, you have the partially expanded steam going back to the boiler, basically to pick up more heat. That's called reheating. And then going back with even higher temperature and pressure, no, even higher temperature. The pressure does not change going through the boiler. So higher temperature, then going into the low pressure turbine. So in that case, you will end up with a higher steam quantity. This will be clear if we draw the TS diagram. Right, so we have state 1 to 2, then to 3, then going through a partially expanded turbine, which is a high pressure turbine, to a lower pressure line, and then being heated again, going up again to the state 4, 5, and then going back to the state 6. Right. The difference compared to not using a reheater is if you are not using this step, it will end up with this, which means you will end up with a much larger moisture in the at the end of the turbine. So in terms of calculation, we would have the turbine work is two component, which is H3 minus H4 plus H5 minus H6. And the pump work is V1 P2 minus P1. And the heat input is also two parts, which is H3 minus H2 plus the H4 minus H5 minus H4. Right? Then the efficiency of this reheated Rankine cycle is just the WT minus WP divided by the total heat input. So I should mention that this reheating is not necessarily giving you higher efficiency. The reheated Rankine cycle is not necessarily giving you higher efficiency. So if you're looking at here, you're adding more heat into the system and you're producing more work. If you still remember the work corresponding to the area enclosed by the states of the cycle. So the work corresponding to 1, 2, 3, 4, 5, 6, this irregular area, that's the work. And the heat corresponding to the area underneath 2 to 5. So the total area corresponding to the heat input. You gaining more work, you also input more heat. It's not necessarily helping you in terms of efficiency, but reheating is used commonly in combination with the high pressure. So we said when you're using high pressure, you can have high efficiency. But you have high pressure, you have the problem of the low steam quantity problem. So you're using reheat together with high pressure in order to get the high efficiency. That's what practically used. So the purpose, I should say, to increase steam quantity to allow higher boiler pressure. And also, in terms of the TS diagram, we have seen this type of feature before in the cycles that we learned before. Do you recall where we have seen this? From the 4 to 5? We have seen that more than once, actually. Twice. Jet engine of what? Afterburner, yes. Afterburner is one place that we saw this, and I heard regenerator. Yeah, regenerator is not giving, regenerate do not have additional heat added. Reheater, yes. Reheater is a place you add additional heat. But all the three, the turbojet, the reheater in the Brayton cycle, and here they are working for different function or the different purpose. Right? So here the purpose is mainly to improve the steam quality. Right? So to push this horizontal line to the right, so that you end up with a higher quality of steam. But in the turbojet, the afterburner is to give you additional thrust. You're adding more energy right before the nozzle so that you can produce higher thrust for the emergency taking off condition. And what's the purpose of reheater in the Brayton cycle? In that case, the purpose actually is to maintain a large specific volume of the gas during the expansion, so that we can have a larger work output from the turbine, from the gas turbine. So if I have again related to this equation, during expansion, if you keep this specific volume as large as possible, you will have a large work output from the turbine. Right? So they all, looking at the TS diagram, they are the same feature, but they all being used for different purpose. All right, so that's one commonly used or modification of the basic cycle, which is reheated Rankine cycle, and another one, which is also commonly used in reality, is called the regenerative Rankine cycle. So the regenerative is something we heard before when we were talking about the Brayton cycle, right? And in that case, that the regeneration is to, anyone recall what's the purpose of that regeneration? That's a heat exchanger where you're using the turbine exhaust to heat the compressed air before it getting into the combustor. So you utilize some of the waste heat in the turbine exhaust to preheat the compressed air, so that you can add a less amount of heat at the combustor to reach the same temperature. All right? So this is a similar idea, is to certainly reduce the amount of heat you add into the system. And how this process works is you do not allow all the steam to fully expand at the turbine. So similar to this case, the reheated case, you're using multi-stage turbine and have certain turbine which is partially expanded, and certain steam to partially expand it, and using that steam as a heat source to heat water before it going into the boiler. Right, so the schematic here, There are two types. One is called the open feed water heater, and the other is a closed feed water heater. But we can just look at one and understand how it works. So you have the turbine. Here actually do not necessarily using two turbines. You're just using one turbine and direct some of the partially expanded steam to basically the heat exchanger. This is an open feed water. It's called open because you do not using shear tube type of heat exchanger, but just using a mixing box or mixing chamber. So you have the steam coming in as a vapor, superheated vapor, right? And then you have the compressed water coming in, and the temperature of the steam is higher than the water, so that we'll have the mix and then have the heat transfer. And ideally, at the exit of this mixing chamber, you will have saturated water. All right, and that water then being compressed again, then getting into the boiler, and then going through that process. So this is called open feed water heater. So it's one type of regenerative Rankine cycle, and the other one is called closed feed water heater. So the only difference is here you are not using a mixing chamber. You do not allow the steam and water to see each other. Rather, they flow in their own path. So the water is flowing in the tube, as shown there, and the steam is just flowing on the outside the tube. So they can still have the heat transfer, but they do not reach the same pressure. For the open feed water, they must reach the same pressure because they see each other for the mixing. All right, so we can draw the TS diagram for each of these. It's more complicated, but if you understand how the process goes, that's not that. It's certainly not that difficult. So let's do this open feed water first. Try see if I can show both at the same time. I tried to draw a TS diagram for the open feed water case. So in this case, and we have an intermediate pressure in the middle. So all right, let me use different color. All right, so if we're starting with state 1, which is consistent with what we said before, the state 1 is the inlet of the pump. So we have the state 1 there, and then going up to the state 2 there. If you can. All right, state 2 there. And then that's the inlet of the feed water heater. And then let's work out the other stream first. So if we go from the other side, which is the turbine inlet, let's go for the turbine inlet, which is a state 5 there. Then it's supposed to go all the way down, but leave the turbine earlier, which is at state 6, and then end up with state 7. All right. So there, instead of continue expanding, it going towards to mix with this compressed water. All right. So they go together and then meet, ideally at this on the edge of the saturation dome, which is the state 3. at exit, you reach the saturated liquid, and then going through another pump to the boiler pressure, which is state 4. Right? So that's, you have two streams come together to state 3, then going up. So like this. So this type of cycle is only one thing is a bit tricky, is the mass for the different stream you need to know. Right? So if I have 1 kilogram of working fluid, and I assume there is a fraction of it, like a y kilogram of working fluid being bypassed here. So total is 1. A fraction of it going bypass the turbine. And then how much is this line? 1 minus y. Yep. And this line, y or 1. Yep. This is where the two streams join together, and then going through the boiler. Right. So in terms of calculation, you need to pay attention that each energy term, heat or work term, that have a mass fraction attached to it. Right? So if I want to calculate the total turbine work, I should say this open feed water heater, right? The turbine work is 2 parts, right? It's from the H5 to H6 and plus the H6 to H7, right? So H5 to H6, that's what coefficient should I times? That's a total mass. And in this case is 1 minus y for the rest, right? So that's how you calculate the turbine work. And then for the compressor, pumping work from the V1 P2 minus P1, the coefficient I should times is 1 minus y, right? And the one for the upper second pump, which is V3 P4 P3, that should be 1. And the total heat input is H5 minus H4, and that should be 1 as well. Right? Then you just calculate the efficiency, which is again WT minus WP Q in. All right. I think that's it's time to stop. So let's continue Tuesday.